Hi there. So in this lesson, we're going to start learning about the basics of trigonometry, actually getting into trigonometry. Now this lesson might seem a little bit strange because what we're going to focus on are what are called the definitions of right triangle trigonometry functions. Okay, and so we just got to get some basic definitions down. And there's not a whole lot of application with what we're going to do today, but these definitions are very important to understand and to get down. There's actually 6 of them to get down. There's 3 basic ones and then 3 related to the first 3. All right, and the key thing is to try to get these down because once we start doing things in a more practical sense, having down those definitions are going to be critical for how we set up problems. All right, so here we go. Now, the one thing we got to first do is talk a little bit more about similarity. All right, and so notice that these 2 triangles that I've drawn, or I'll just give you that they're similar if it's not completely obvious. But let's say that these are 2 similar triangles. Okay, so remember, similar means they're shaped the same but different sizes. And the way we can determine is from the angles. If all the angles are equal, then the 2 triangles have to be similar. Okay, and so say I label this side A, this side B, this side C, and then just keep following the alphabet here. Okay, now if you remember from last time, whenever we talked about similarity, we said that ratios of corresponding sides are equal. And that's true. We're going to do it slightly different whenever we get into trig though. So what that said is that A over D was equal to B over E, and that also is equal to C over F. Okay, but what we can also do is look at basically corresponding sides on each triangle. So I could look at the ratio of A over C. Okay, like that. So what is A over C? In terms of the sides of the triangle, A is the side that's opposite the 3-arced angle, and C is the side that's opposite the 2-arced angle. Okay, and so what that ratio has to equal is the same kind of relationship over in the big triangle. So the side opposite the 3-arced angle and the side opposite the 2-arced angle, and so this would also equal to D over F. Okay, like that. And if we follow that pattern, I could say that A over B is equal to what, to the ratio of what 2 sides? That would be D over E. And then thirdly, the last one is I could look at the ratio of B over C, all right? And that's going to be the same as the ratio of E over F. Now, one other thing to point out too is whenever we set up ratios like this, we can set them up either way. You know, if you remember, these are called proportions, and we could set them up either way, meaning that I could flip all of those over as long as I keep things lined up. So I could rewrite that first equation as D over A equals E over B is equal to F over C. Okay, like that. Sorry, I made a little mark there. I didn't mean to. All right, what that's going to allow us to do, if you remember a minute ago, I said that there's 3 basic trig functions definitions to get down, but there's 3 related to them. The 3 that are related to them involves doing what I just mentioned, basically flipping things over in these relationships right here. Okay, so I've mentioned this before. Everything about, especially right triangle trig, but trig in general, is about similarity. Okay, it's just kind of a summary of a lot of similarity relationships. So similarity leads to right triangle trigonometry. Okay, so let's look at this triangle I have pictured right here. And so say I tell you that that's a right angle. So this is called a right triangle. And that's why it's called, what we're about to get into is called right triangle trigonometry, because we're going to use right triangles to define everything. Okay, so say I know that, and then I also know an angle. Or signify a given angle. Okay, it doesn't matter which other one. Now we already know the right angle, so we're talking about one of the other 2's. So for now, let's say I'm talking about this angle, and I'm just going to call it theta. We don't need to worry about how big it is right now, okay, to get these basic definitions down. All right, like that. Now imagine another right triangle that also has the angle theta in it. Okay, like that. And so let's think about that a second. Let me get us a picture of one here. All right, so here we have a right triangle. It's drawn a little bit differently, but the key thing to notice here is that it does have a right angle, and it also has this angle theta in it. All right, well, what can we say about those two triangles? And if you have trouble seeing it, the first thing you might want to do is redraw this triangle. So I changed the size a little bit, but that's not terribly important. Okay, but let's have them where they're looking, where they have the same base. What can we say about these two triangles, though? Okay, and hopefully, I mean, at least looking at the shape, they look shaped the same. They're just different sizes. Okay, uh, so the question right now is, are they similar? Like that. And the answer is yes, okay? Because you can just kind of reason this out. Say, if I know the right angle and I know this angle theta, remember the angles in a triangle add up to 180 degrees. So I could calculate this angle right here based off of those two, all right? And, you know, if you're having trouble seeing, let's just pretend like theta is 30 degrees right now. Okay, so here's 30 degrees, here's 90 degrees, and so 30 plus 90 is 120, so this angle would have to be 60 degrees, okay, for them to add up to 180. And see, I could go through the same thing with this bigger triangle. Here I have 90 plus 30 again, that's 120, so this angle would have to also be 60. All right, so these two angles right here are equal to each other. So there's no question about it anymore. These two triangles are similar to each other. So yes, they are similar. Now one other thing too is I just drew that, or you know, I copied it in, but I just drew that second triangle in there. So it doesn't matter what the size of this triangle is. It could be little like that. It still has that right angle and it still has that angle theta. So this angle would have to be the same. So these two are similar to each other. And then I could really make that triangle big. All right, same thing. This triangle right here is is similar to this triangle right here. Okay, so the size of that triangle doesn't matter as long as I have that right angle and that angle theta in there. Those two triangles are similar to each other. So what I'm trying to get at here is all right triangles with the given angle theta. They're all similar to each other. Okay, so there's this huge infinite set of triangles that are all similar to each other. They're all right, they all have a right angle, but then the other distinguishing factor of them is that they all have that shared angle theta in them. And that's where it's going to lead into right triangle trigonometry. All right, so sticking with this same right triangle right here, what I can do is I can label the sides of this triangle based on our right angle and our given angle, okay? So first of all, this is true anytime. Anytime you have a right triangle, here's your right angle. The side that's opposite that right angle is always the longest side of the triangle. And if you remember, we call that the hypotenuse, all right? And so we're going to label that side height for hypotenuse. Okay, now so that'll be true in any right triangle. You can always identify the hypotenuse regardless. Now these other two labels depend on the angle theta that I'm talking about. Okay, the labels will be different if I'm referring to this angle up here. So I got to be referring to just one given angle here. Okay, but just like the hypotenuse is opposite the right angle, then what I do is I look at the side that's opposite the given angle theta. Okay, and I'm going to label that as the opposite side. We'll abbreviate it as op, like that. All right, and so be very careful about this labeling because it depends on what angle you're talking about. All right, but then I'll explain this. Then the third side of the triangle will label ADJ, and that stands for the adjacent side. Adjacent means next to. And so whenever you have this given angle theta, there's two sides that are next to theta, but one of them will be the hypotenuse. So we're talking about the other side that's adjacent to theta. All right, so that's the way I like to label. Is I find the hypotenuse, then I always label the opposite side first, and then I just say, well, then the third side's going to be the adjacent. Okay, some people like to do it just the opposite. Then you always identify the hypotenuse first, but then the adjacent will be the other side of that angle, and then in that case, just the third side would be the opposite side. So that's kind of up to you how you recognize it first. Now make sure you realize too, if I take that same triangle, okay, but instead of designating the angle that we did, if I designated this as my angle theta, the hypotenuse will stay the same, but the opposite side becomes over here, and this becomes the adjacent side, so they reverse. All right, so whenever you're doing trig, it's important to label sides based on what angle you're talking about. Okay, and so that ends up being important and something you got to be very careful of. I just wanted to point that out. Now let's get into the actual trig definitions. Okay, so here's the idea. So let's think about having these two right triangles. All right, and so this is a right triangle too, and they have that same angle theta. Okay, so in terms of the labelings, they would have the same things. Now make sure you realize the size of these are different. So let's call this hyp star and op star and adjacent star. So these individual lengths right here are different, okay? The hypotenuse here is shorter than the hypotenuse here. The adjacent side here is shorter than the adjacent side here, etc., etc. Okay, so we do have that situation, but those two triangles are similar, okay, like that. And so they're similar to each other. And so what that means is that if I measure the ratio of the hypotenuse, well, I said that backwards for what I'm trying to get at though. If I measure the ratio of the adjacent to the hypotenuse on the smaller triangle, it's going to be the same as the adjacent to the hypotenuse on that larger triangle, like that. And the key thing here is that it doesn't matter what size this other triangle is, that same thing is going to happen. Okay, if it's really small, you're still going to have those equal ratios. If that triangle is really large, you're still going to have those same ratios equal to each other. Okay, so this ratio right here is common to all right triangles that have that right angle theta and that right angle and that angle theta in them. Okay, and so we give a special name to that ratio right there. That's called the cosine of theta. Okay, like that. And we abbreviate that as just cos theta, but we say cosine of theta. All right, like that. And so what cosine of theta is, the definition of the cosine of theta, it's just that ratio of the adjacent to the hypotenuse in any right triangle that has that angle theta. All right, and so that's the idea. And similarly, we're going to see that we can define what's called the sine and the tangent, just using different sides though. All right, so let's go to the next slide to do this. And before I carry on though, the role of this angle theta is important. So we always write it, okay, even if it's not known. In this right now, when we're trying to get the definitions down, we won't give theta a value. Whenever we start using it practically, we will know what theta is though. But the idea here is that this label right here, adjacent, depends on what angle in the triangle I'm talking about. So that's an important thing to keep up with. Okay, so I'm being a little bit repetitive on purpose, but if we have a right triangle with this angle theta, then the ratio of the adjacent to the hypotenuse is always the same. So we call that the cosine of theta, and we abbreviate it cos of theta, but we say cosine of theta. And what the definition of what the cosine of theta is it's the adjacent to the hypotenuse. Okay, and so we get two other functions based on the other sides. We can talk about the sine of theta, all right, and we abbreviate that sin. one thing to know though, there's no sins in math, so we say sine, not sin. All right, and what that is that's the ratio of the opposite to the hypotenuse. Okay, like that. And so what we're doing is we're looking at all the combinations of ratios we can get. So here's two sides we've compared to get for the cosine. Here's two sides we've compared to get the sine. And then what we need is a function to compare these sides right here. And we call that the tangent of theta. And we abbreviate that TAN. And what that is it's the ratio of the opposite to the adjacent. Okay? And those are the three basic trig definitions right there. Now, we could be talking about a different right triangle too. All right? And so make sure you realize the angle could change. That didn't come out very right, but let's just pretend, just to save some time, let's say that's a right angle right there. And so here I could call this angle theta, and it's gonna, the angle's different, so the triangle's gonna look different, but we would still say that the cosine of that angle is the ratio of its adjacent to its hypotenuse. Now, you may be saying, why did I look at adjacent over hypotenuse instead of hypotenuse over adjacent? Okay, and we could have done things that way. This is just the standard way to do things, and it'll lead to some properties that are nice about the cosine and the tangent, or the cosine and the sine especially. But we can look at the ratios that are the reciprocals of the ones we given, and those lead to the other three trig functions. Okay, and so there's what's called the secant of theta. And we abbreviate that SEC of theta, like that, and that's the reciprocal of the cosine, so it's hypotenuse over adjacent, okay? And the way I always think about these is I know which one's the reciprocal of which. So secant is reciprocal of the cosine, okay? And then there's the cosecant, okay? And so and we abbreviate that CSC of theta, and that's the reciprocal of the sine, so it would be hypotenuse over opposite, okay? And then the third one, or the sixth one, if you want to think about it that way, is the cotangent of theta, okay? And we abbreviate that COT of theta, and that is the reciprocal of the tangent, so adjacent over opposite, like that. So anytime you're asked to give all 6 trig functions, this is just the way I do it. You can do it the way you want, but I know which one's reciprocal of which. And so, and I'm going to do an example like this in just a moment. But if I'm asked to give all 6 trig functions, I'll find the cosine, give the 2 numbers that go in right here, but then right next to it I'll say what the secant is, and all I do is flip these 2 numbers over to get me the secant. And then the sine, I'll find the sine, fill in the numbers here, and then I know cosecant is the reciprocal, so then I just flip those over to give the cosecant, etc. with the tangent. Now, as far as keeping up with them, which one's reciprocal of which, notice the tangent and the cotangent go together, okay? But then notice that I have these basic root words. And the root word in both of these is sine, just one of them doesn't have that prefix, and one of them has the prefix co. All right, same thing down here. We have secant and cosecant, so the root is secant, and then one of them has the co. And the reciprocal pairs go in, see, notice that the reciprocal of the cosine is the secant. So one pair has the co prefix, one does not. Okay, that's it. I don't know if that's the clearest explanation, but that's the way I keep them in my mind. Is if I'm being forgetful and I'd say cosine of theta, and then I wonder which one's the reciprocal, I know its root has to be secant, and since this has a co on it, then the reciprocal of this is just secant. All right, it doesn't have that co on it. So yeah, let's look at some examples to try to make this a little bit more concrete. Now, one thing to point out too, what we're doing right now isn't practical. It will be practical once we incorporate angles, but right now we're just mostly getting down these definitions because it's a lot to try to absorb. So we're really just practicing getting down those definitions. So whenever we do start doing things, practically, then we're not finding and trying to remember the definitions. Okay, so anyway, we're going to find the six trigonometric values of the trig functions of the given angle theta in the picture, and we'll do a couple of these. So here's the first one. This is a very common type of right triangle called a 3, 4, 5. Those three numbers form what's called a Pythagorean triple, and so this forms a right triangle here. Anyway, so to get started, we're trying to find the value of the six trigonometric functions. So we need to say what the cosine of theta is, what the sine of theta is, what the tangent of theta is, and then the other three would be the secant of theta, the cosecant of theta, and the cotangent of theta. So that's what we're trying to do, is give those the value of those trig functions. Okay, now remember, to do this, like the cosine is the adjacent over the hypotenuse. All right, like that. And so we need to identify what these sides are. All right, so remember how we get started. Here's the right angle. The side that's opposite the right angle is the hypotenuse. So this 5 is the hypotenuse. All right, and then we need to label our opposite and adjacents. So here's theta. The way I do it is I say, here's the side opposite theta. So 3 is the opposite, and so 4 is the adjacent. Okay, like that. And so the adjacent over the hypotenuse here is 4 over 5. You see that? Okay, adjacent over hypotenuse, 4 over 5. And then for the sine, it's opposite over hypotenuse. Okay, and our opposite side is 3, and our hypotenuse is 5. All right, and then for tangent, it's opposite over adjacent, like that. And so the opposite side is 3, and the adjacent side is 4. Okay, now like I said a moment ago, if you write the reciprocals next to, or the reciprocal functions next to their corresponding reciprocal, then this part right here is easy. All right, we just flip them over. So the secant's the reciprocal of the cosine, so it's 5 over 4. The cosecant's the reciprocal of the sine, so it's 5 over 3. And the cotangent is the reciprocal of the tangent, which is 4 over 3. Now, you don't have to do these this way. You can use the definitions and fill numbers in just like we did here, whichever way you are most comfortable. All right, so let's look at this example right here. So we have a right triangle, although I didn't draw it very well. Here's my angle theta, and then one side is 2 and one side is 7. Now, anticipating what we're going to do, you might notice something's a little bit weird here. Think about starting to label the sides. Here's your right angle. The side opposite it is 7. So that's the hypotenuse. All right, but what's wrong here? When I go and try to label the opposite, it's not there. Okay, like that. So we don't know what that opposite side is. All right, but this 2 is the adjacent. It's the third side. So ask yourself, how would you find that opposite side? Well, we have a right triangle, so we can use the Pythagorean theorem to find it. Okay, so let's call this side x instead of a question mark. So what are we going to have from the Pythagorean theorem? We're going to have x squared plus 2 squared is equal to 7 squared. So x squared plus 4 is equal to 49. So x squared is equal to 45. So x is the square root of 45, but you should always ask yourself if that thing simplifies. 45 is 9 times 5, and 9 is 3 times 3. So notice I have that pair of 3's that I can take out. So I get 3 square root, and then there's a 5 left behind underneath the square root. Okay, so to summarize all this, our hypotenuse is 7. Our opposite side, now we know it, is 3 square root of 5. And our adjacent side is 2. All right, so now we're ready to answer the question. Start with the cosine of theta. That's the adjacent over the hypotenuse. I would advise, as you're learning this, just to keep writing those definitions, and just so it helps get them ingrained in your brain. All right, and so that's going to be 2 over 7. All right, and then for the sine of theta, it's opposite over hypotenuse. Okay, which is 3 square root of 5 over 7. For now, don't worry about getting the decimal forms. Just keep everything exact. what we'll see is once we get to the reciprocals, we're going to have to do some rationalizing. Okay, and so tangent is opposite over the adjacent. That opposite over adjacent is 3 square root of 5 over 2. All right, so we need to go to the reciprocals. And so for my reciprocals, the secant is reciprocal to cosecant. So just remember that with reciprocal pairs, only one of them has that co-prefix. So I accidentally started to write cosecant right here, and I instantly caught myself because I would have had two cos as reciprocals. All right, and so the reciprocal of 2/7 is 7 over 2. All right, now for our cosecant, we're going to have to do a little bit of work because its reciprocal is 7 over 3 square root of 5. But we have that square root of 5 in the denominator, so I want to rationalize it out. And so I'm going to get 7 square root of 5 over 3 times 5. Okay, like that, which would be 7 square root of 5 over 15. All right, so that one ran a little bit long, so to go to the cotangent here, hopefully you'll be doing this on paper where you have more room, and so you won't have to do this. Maybe that's a little bit sloppy, but reciprocal, cotangent is the reciprocal of the tangent, so we got 2 over 3 square root of 5, same thing as last problem. We rationalize out that square root of 5, so we'll have 2 square root of 5 over 15. All right, and so there's the 6 trigonometric functions of that angle. All right, and here's another type of problem we can play around with, is that if I'm giving one trig value and I'm given that the angle is acute, I can find the value of the 5 other trig functions, and we'll see how to do that in a moment. Okay, there's a couple things to point out about these definitions. But to get started, you might want to pause a second, and I'll give you a chance to see if you can think about how you would solve this. But anyway, hopefully you did, and hopefully you saw. But the idea here is that I have a triangle, and its tangent of one of its angles is equal to 3/5. Okay, and so remember from the definition of the tangent, this would be this would be an opposite side, and this would be an adjacent side. Okay, like that. And so what I can do is I can just draw myself a right triangle. You don't have to worry too much about it being perfectly to scale. Okay, like that, and just call this angle here alpha. And so one picture of this is with the opposite side equal to 3 and the adjacent side equal to 5. And then like last example, we'll use the Pythagorean theorem to find x. Just one small point to point out. Remember, trig is all about similarity. So whenever I say that the tangent of alpha is equal to 3/5, this really isn't the only triangle that fits that description. Okay, that's a similarity ratio. So this side could have been 6 and 10. Okay, and then when I wrote opposite over adjacent, I would have got 6 over 10, which reduces to 3/5. And see, that's what similarity is all about. So all we're doing is drawing one representative triangle that fits that description, but there's actually infinitely many triangles whose tangent of alpha is equal to 3/5. They just the ratio of the opposite and over adjacent always reduces down to 3/5. But anyway, if that's too much information for you, it's all right. Okay, but anyway, just to find x here, we use the Pythagorean theorem. Make sure you realize x is actually the hypotenuse here, so we're trying to find the hypotenuse. Let me go ahead and put these in just for whenever we do finish the problem. Okay, but anyway, the first thing we need to do is find x. Since it's the hypotenuse, the Pythagorean theorem would say that 3 squared plus 5 squared is equal to x squared, like that. And so I have 9 plus 25 is equal to x squared. 9 plus 25 is 34. And so the hypotenuse, or x, is equal to the square root of 34. Okay, so there's some side work for us, but now we know what that opposite side is. I'm sorry, what that hypotenuse is. So we have the hypotenuse is the square root of 34. The opposite side is 3, and the adjacent side is 5. Okay, like that. And so we can go to the other 5 trig functions. The cosine of alpha is adjacent over hypotenuse. Okay, I can already see I'm gonna run out of room if I'm writing here, so I'm just gonna go down here lower and do this. So we have the cosine of alpha is the adjacent over the hypotenuse. Okay, and so the adjacent side is 5, but my hypotenuse is the square root of 34. So I got to rationalize out that denominator. And so we end up getting 5 square root of 34 over 34. All right. Now I want to show you something now. You can go down and continue with the sign, or what I usually do is I just find the reciprocal function now. Now one thing here, you got to, if you do some thinking, you can just take the reciprocal here, but you're going to have to rationalize again. But you got to realize where this came from. It came from 5 over the square root of 34, like that. And so if I reciprocate this, if I take the reciprocal of this, that square root's going to automatically get put up in the top. And so I won't have to rationalize. So I could just say this is the square root of 34 over 5, like that. All right. And then the sine of alpha is going to be the opposite over the hypotenuse. Okay, the opposite is 3, and the hypotenuse is the square root of 34. Again, I'm going to rationalize. Hopefully it's been getting to be a little bit repetitive already about how to rationalize, I mean. Like that. And so then, to get to its reciprocal, the cosecant, all right, again, it would be, you can take the reciprocal of this, but you're going to have to rationalize and reduce. Remember what we started out with, 3 over the square root of 34, so that's the easier one to take the reciprocal of. Okay, now if I'm given one of them, I still write it just to help me, and especially if I'm going to have to find its reciprocal. So the tangent of alpha is 3/5, that was given to us, and so that would make the cotangent equal to 5/3. Like that, and there's the 6 trigonometric functions of that angle. Okay, there ends up being a nice relationship for the sine and cosine based on what are called complementary angles. Okay, complementary angles are 2 angles that add to 90 degrees. Okay, like that. All right, and so we're just talking about 2 angles, and then they add up to 90. Now let's look at a right triangle. Okay, let's call this angle A, or let me just keep getting you used to Greek letters. So let's call this angle A, and this angle alpha, and this angle beta. Okay, like that. And what I'm going to do is I'm going to make a copy of it that you'll see why in just a moment. All right, and so I need to get a copy of it on here. So we have it, so don't worry too much about that copy right now. Okay, but let's think about this, all right? So remember that the 3 angles in a triangle have to add up to 180 degrees, right? So that means that alpha plus beta plus that right angle, so that's 90 degrees, has to equal 180 degrees, right? Like that, and then if I subtract 90 degrees from both sides, I get that alpha plus beta is equal to 90 degrees. What's significant about that, i.e., they're complementary. That's what complementary angles are, okay, like that. And so one thing to realize is that the angles in a right triangle, the other angles, I could say more correctly, the other angles in a right triangle are complementary. That should be fairly obvious. Okay, like that. Now let's take these 2 pictures right here. Oops. So let's take these 2 pictures and let's move them down here. So what I'm going to do is I'm going to give these sides letter names too to help you see something in a minute. So I'm going to call the vertical side A, the flat side B, and the height and that longer side C. Now these are the same triangles, so these letters will be the same over here. Okay, now for in the first triangle, let's ignore beta for right now. Okay, so let's see what, and label the sides based on alpha. Now in both of these, C is the hypotenuse. Remember, it doesn't matter about angles about which side gets the hypotenuse. All right, but in this first triangle, if we're talking just about alpha, then where's its opposite side? It's over here at A, and so B will be the adjacent side. Okay, like that. And so then, what do we get then? Then if I say what the cosine of alpha is, it's the adjacent over the hypotenuse, so that's going to be B over C. All right, and then the sine of alpha is the opposite over the hypotenuse, so that's going to be A over C, right? Like that. And now let's go over to the same triangle, but let's ignore alpha this time. Okay, like that. Do you see that the labeling reverses around? The side opposite beta is B. So now this becomes the opposite side, and A will become the adjacent side, like that. And so if I do the cosine of beta, like that, if I do the cosine of beta, then that's going to be adjacent over hypotenuse, so that's going to be A over C. And the sine of beta is opposite over hypotenuse, and so that's going to be B over C. Now, why am I pointing all of this out? Is look here, where are things equal? The cosine of alpha is equal to the sine of beta, and the sine of alpha is equal to the cosine of beta. All right, and so that's what I'm trying to get at here is if I have two complementary angles, any two complementary angles, if they're complementary, like that, then the cosine of the first is equal to the sine of the second, and the sine of the first is equal to the cosine of the second, like that. And that might seem a little silly to point out, but there are times every once in a while where you'll want to switch things over to the other trigonometric function. So say for some reason I have an expression that involves the sine of 28 degrees, but I want to get it in terms of the cosine of something like that. Well, the equivalent cosine that it's equal to is it's the angle that's complementary to 28 degrees, like that. All right, you could set up an equation. Some of you know that you would just subtract from 90, but then our angle there would be, so then 28 degrees plus whatever this angle needs to be right here would need to add up to 90 degrees since they're complementary. And so then I could subtract 28 degrees like that, and I get beta is equal to 62 degrees, like that. And so what we could say is that the sine of 28 degrees is equal to the cosine of 62 degrees. All right. One other thing too, this is a small fact, but just why I thought about it, I haven't explicitly said it. Make sure you realize in a right triangle, because all the angles have to add up to 90 degrees, 180 degrees, but we've already used up 90 degrees, okay, because of that right angle. So these two angles, they add up to 90, like we said, they're complementary, all right? So you have these two angles that add up to 90 degrees. Make sure you realize, since we're forming an actual triangle there, these both have to be smaller than 90. Okay, and if you remember what we call an angle that's smaller than 90, i.e. acute. So it's just a nice thing to keep in mind, just in case you make a mistake. Anytime we're dealing with right triangles, now with general triangles this isn't true, but anytime we're dealing with right triangles, all the angles are acute, i.e. they're less than 90. So I'm going to leave that there for now. Like I say, this lesson right here isn't very practical. There's not a whole lot of practical things we can do with it. But trig is very practical, especially this geometric part of it. And the key thing is to get those definitions down so that you don't accidentally use the wrong one. We'll mostly just use the main three trig functions, sine, cosine, and tangent. And then the way I know the other ones is I just memorize them as the reciprocal of whichever one it's the reciprocal of. And so, but you want to get those definitions down, so make sure to practice that. And otherwise, I hope that helps and makes sense. Let me know if you have questions, and all the best.